Welcome back. In this section, we will cover the basic programming syntax in assembly language. The topics for this lesson are: first, performing data transfers; second, performing simple arithmetic; third, performing data-related operations; fourth, the rules of indirect addressing; and finally, how to force branching with jumps and loops. Let's begin. Assembly programming follows a specific syntax structure that allows low-level interaction with the CPU. We'll walk through the fundamental programming constructs in x86 assembly using the NASM syntax. Let's start with performing data transfers. What is a data transfer? A data transfer is an operation that moves data between registers, between memory locations, or from a constant value into a register or memory. The most common instruction for this is the MOV instruction. For example, MOVEAX, 5 moves the immediate value 5 into the EAX register. MOVEBX, EAX prime copies the value from the EAX register into the EBX register. AMOV square bracket var square bracket EAX prime stores the value from EAX into a memory location labeled var. MOVEAX square bracket var square bracket loads the value from the memory location var into the EAX register. A couple of notes. You cannot move data directly from one memory location to another. You must use a register as an intermediary. Also, always remember to use square brackets for memory access. Next, let's look at performing simple arithmetic. The common arithmetic instructions are A, D, D, EAX, 2, which adds 2 to the value in EAX. E's, U, B, E, B, X, 1, which subtracts 1 from the value in EBX. I, N, C, E, CX primes, which increments the value in ECX by 1. EDE, DX prime, which decrements the value in EDX by 1. For multiplication and division, let's say we want to multiply 5 by 2, we would write MOVEAX, 5, MOVEBX, 2, IMULEBX prime. This performs a signed integer multiplication of EAX by EBX and stores the result in EAX. For division, let's divide 10 by 3. We would write OVEAX, 10, OVEBX, 3, XOREDX, EDX prime. This clears the EDX register, which is important because it will hold the remainder. ED, IV, EBX prime. This divides the value in EAX by EBX. After the division, EAX will hold the quotient and EDX will hold the remainder. Now for performing data-related operations. To compare values, we use the CMP instruction. For example, CMP EAX, EBX promise compares the values in EAX and EBX and sets the CPU flags accordingly. This is used with conditional jumps, which we will cover later. To exchange the contents of two registers, we use the XCHG instruction. XCHG EAX, EBX swaps the values in EAX and EBX. There are also logical operations which are useful for bit manipulation. ANDE AX, 0XFF performs a bitwise AND operation. OREAX, 0x01 performs a bitwise OR operation. XOREAX, EAX prime is a common way to zero out the EAX register. No TEAX performs a bitwise NOT operation, flipping all the bits. Let's move on to the rules of indirect addressing. What is indirect addressing? Indirect addressing is when a register holds the memory address of the data rather than the data itself. This allows for flexible memory access and is especially useful for arrays and pointers. For example, movesi, myvar loads the address of the variable myvar into the ESI register. moveax, square bracket, ESI square bracket. Then indirectly loads the value at the address pointed to by ESI into the EAX register. A key concept here is that square brackets always mean the memory at the address inside. You can also combine registers with offsets. For example, moveax, square bracket ESI plus 4 square bracket will load the value from the memory address, calculated by adding 4 to the value in ESI. This is useful for array indexing. There are several addressing modes. Square bracket reg square bracket accesses the memory pointed to by the register. Square bracket reg plus offset square bracket accesses memory at the register's address plus an offset. Square bracket reg1 plus reg2 square bracket accesses the address from the sum of 2 registers. And square bracket reg1 plus reg2 plus offset square bracket allows for even more complex access, like with structs and arrays. Here's a full example. In our data section, we define an array of double words. My array DD 10, 20, 30, 40. In our text section, we write O VESI, my array. This points ESI to the first element of the array. MOVEA x, square bracket, ESI plus 8 square bracket. This will load the third element of the array into EAX. Since each element is a double word, which is 4 bytes, the third element is at an offset of 2 times 4, which equals 8. Finally, let's cover how to force branching with jumps and loops. What is branching? Branching allows a program to change its execution path, similar to if-else statements or while loops in high-level languages. In assembly, this is done with jump and loop instructions. There are different types of branch instructions. First, the unconditional jump, JMP. This immediately redirects the program execution to a different label. For example, JMP, start, over. Second, conditional jumps. These jumps are taken only if certain conditions based on a previous comparison are met. G jumps if the values were equal. GNE jumps if they were not equal. JG jumps if the first value was greater than the second. J jumps if it was less. JGE jumps if it was greater than or equal to. JLE jumps if it was less than or equal to. Third, the loop instruction, LOOPI. This instruction decrements the ECX register and then jumps to a label if ECX is not 0. Let's look at a jump and compare example. OVEAX, 3. CMPEAX, 5. JL less than. This will jump to the less than label because 3 is less than 5. If the jump is taken, the code continues at less than, where we have MOVEAX, 1. If the jump was not taken, the program would have continued to MOVEAX, 10, and then jump to done. Some tips to remember. Always define your labels before you jump to them. Use a CMP or TST instruction before a conditional jump. And the LOOP instruction always uses the ECXE register as its counter. This concludes our lesson on the basic programming syntax of assembly language. Thank you.